All right, today we're going to go on a journey that's, well, it's more epic than you might think. We're not traveling through space, but through deep time. We're going to uncover the surprisingly dramatic and violent life story of a single rock.
To really get our heads around this, let's start with this key idea from the petrologist John D. Winter. He really hits on something crucial. Our planet is not some static, boring ball of rock. No, it's a dynamic, churning, planet-sized factory that is constantly building and rebuilding the very ground under our feet.
You know, it really makes you think, what if that random pebble you kick on the sidewalk wasn't just a pebble? What if it's a silent traveler with a history that spans millions, maybe even billions of years? Well, that's exactly what we're going to dive into, the secret life of a rock.
To understand a rock's life, you really have to think like a detective. The geologists who study this stuff, petrologists, are basically geological detectives. They don't have witnesses, they don't have crime scenes, all they have are the rocks themselves, and each one holds clues to its fiery, high-pressure past.
Their whole field is built on piecing together a story from scattered clues. They look at a rock's crystals, its chemistry, its texture, and from just those little bits of evidence, they have to figure out the immense heat and crushing pressure that forged it deep, deep within the earth.
So, where does our rock story begin? Well, pretty much every rock story starts in the same place, fire. It begins its life as magma, which is just molten rock formed in the unbelievable heat of the Earth's mantle. But, that brings up a question, right? How does solid mantle rock, which is already incredibly hot, actually melt?
The main way this happens is a process called decompression melting. And honestly, it's totally counterintuitive. You think you'd need to add more heat to melt a rock, but in this case, all you have to do is release the pressure. It's just like taking the lid off a pressure cooker. That sudden drop in pressure lets the superheated stuff inside instantly change its state.
Okay, so here's how it works. Deep down in the mantle, you have this incredibly hot rock that's kept solid only because of the insane crushing pressure. But in places like mid-ocean ridges, where tectonic plates are literally pulling apart, that mantle rock rises really, really fast. As it comes up, the pressure just plummets, way faster than the rock can cool down. And that pressure drop actually lowers the rock's melting point. Suddenly, its own heat is enough to melt it. And just like that, solid rock becomes liquid magma.
And get this isn't some rare little geological quirk. Nope. This one single process, happening right now under our oceans, is responsible for creating about 75% of all the magma on Earth. It is the primary engine building our planet's crust.
Okay, so our rock has been born as magma, but it can't stay that way forever. It's got to cool down, solidify, and take on its first real identity as what we call an igneous rock. But as you're about to see, where it cools down makes all the difference in the world.
So you've got two main ways this can go down. If the magma cools really slowly, deep underground, we call that intrusive. This slow cooling gives it plenty of time to grow huge, visible crystals, like the kind you see in a granite countertop. But if that magma erupts and cools super fast on the surface, we call it extrusive. That creates fine-grained rocks like basalt or even glassy obsidian, where the crystals had literally zero time to form it off.
But sometimes, a rock gets a taste of both worlds. A big crystal, which we call a phenocryst, might start growing while the magma is still deep underground. Then if that magma suddenly erupts, that big preformed crystal gets locked inside a fine-grained matrix that cools around it in a flash. For our geological detectives, these are huge clues about the rock's two-stage history.
But here's where the detective work gets really tricky. If you just rely on those big, obvious crystals, you can be completely misled. A phenocryst only tells you about the first part of the magma that started to cool, not the final chemical makeup of the entire rock. It's like trying to review a whole movie just by watching the opening credits. You're missing the whole story.
So, to get the real story, scientists have to look closer. They analyze the rock's unique chemical fingerprint. They examine trace elements and isotopes. These are tiny chemical variations, atomic signatures, that act like a geological DNA test. This is what reveals where the magma really came from, how deep it formed, and all the crazy changes it went through before it finally hardened.
But wait, the journey is far from over for our rock. Tectonic forces can grab our brand new igneous rock and bury it again, deep inside the Earth's crust. And down there, it's subjected to incredible heat and pressure. Not enough to melt it again, but more than enough to completely change it into something new.
And the key thing to get here is that this all happens while the rock is completely solid.
The original minerals, they just can't take the heat and pressure, so they recrystallize into entirely new minerals, often lining up in layers and bands. It's just like baking a cake. You take flour, sugar, and eggs, you apply heat, and you get a cake. The ingredients are the same, but the final product is a fundamentally different thing.
So geologists have this scale to measure just how intense this transformation was. It's called metamorphic grade. A low-grade rock was sort of lightly baked, while a high-grade rock was cooked and squeezed like crazy. So how in the world can they tell the difference just by looking at it?
Well, they do it by looking for specific index minerals. These are minerals that only form under very specific conditions of temperature and pressure. For instance, if you see a mineral called chloride, you know you're looking at low-grade conditions. But if you find garnet, oh yeah, you know that rock went through some serious heat and pressure. These minerals act like little tiny thermometers and pressure gauges, faithfully recording the extreme history of the rock.
So our rock has been magma, it's been igneous, it's been metamorphic, it's lived all these lives, but its story still isn't over. Because all of these stages are just part of this massive, continuous planetary recycling system. That metamorphic rock we were just talking about, it could get pushed up to the surface, get weathered down into sand, and become a whole new sedimentary rock. Or it could get shoved even deeper, melt all over again, and become new magma, starting the entire cycle over. Melt, cool, squeeze, repeat. It is a powerful cycle that's been turning for billions of years. And this isn't just some abstract textbook concept, you know? This is the very engine of our planet. This is what builds mountain ranges. It creates continents. It's constantly recycling the Earth's crust. The ground you're standing on right now has almost certainly been something else before, probably many, many times over.
This constant recycling builds our world, but it also erases it. With every rock that melts or gets crushed into something new, a tiny piece of Earth's ancient history is wiped clean forever. And that leaves us with this one final, really fascinating question. What incredible secrets of our planet's deep, deep past are being erased, lost forever in this amazing, never-ending cycle?